So, Edson from Red Hat, take it away.
Thank you. Okay. Can we switch? OK. Thank you. Hello, everybody. Good morning. It's a great pleasure for me to be here for the first time in Belgrade. It has been very nice so far. And just in case you're wondering, I'm Brazilian. Not the typical Brazilian you would expect, but I'm a Brazilian Japanese. And my name is Edson Yanaga. I'm a director of developer experience at Red Hat. My Twitter handle is @Yanaga. Just in case you want to follow me, I talk a lot about DevOps, microservices, software craftsmanship, and Java stuff. But today I'm going to discuss with you this topic, migrating to microservice databases, because I've been talking about DevOps and microservices for quite some years. And when I was discussing microservices with people, everybody asked me this exactly same question. If the best practice to create a microservice architecture is to start from a monolith and then break it apart into a microservice architecture, how do I deal with my legacy monolithic database? I didn't have an answer for that. That's why in the past 2 years, I've been researching and discussing with different teams and people worldwide, try to see how they solve this problem. And that the things that I've collected in the past 2 years, I was able to build this session for you. And that's what we're going to discuss today. I also happen to be a Java champion and a Microsoft MVP, which is like an extremely weird combination. But it just shows us that the world has changed a lot in the past 2 years. And many of the concepts that we had before are not true anymore. And if you're interested in that, I just released the book from O'Reilly, Migrating to Microservice Database, which is the exactly same subject of this talk. I even have like a few, 4 or 5 hard copies left that I might be able to distribute in the end of the session. But Red Hat developers bought the royalties of the electronic version. So if you want to download electronic version of the book, you can type this full URL. You can get it for free. Or if you go to my Twitter handle @Yanaga, the pinned tweet has a link to download the book. Okay? And I always like to start my talks with this quote from Forbes. Now, every company is a software company. I like to say that you don't work for a bank, you work for a software company. You don't work for an industry, you work for a software company, because we're all part of what people are saying that is a digital revolution, digital transformation, or digital economy. And I like to say that I like to think about economy, because I used to be one of these people that thought that economics had everything to do about money. But then after reading some books about behavior economics and later behavior psychology, I just realized economics has nothing to do about money, but has everything to do about people. Because at economics, we're studying how people interact with each other and how they change a system from one state to the other. So some motivations that people have to change this system from one state to the other can be love, can be hate, can be power, it can also be money. So when we're talking about digital economy, we're discussing how software is changing the way that people interact with each other. Some great examples of this new digital economy are that the largest car transportation company in the world owns no cars, which is Uber. The largest lodging company in the world owns no real estate, which is Airbnb. The largest online retailer in the world owns no stock, which is Alibaba. And the largest content network in the world produces no content, which is Facebook. All of these companies, they have something in common, is that they only exist because of software, and they are changing the way that we interact with other people. So software is going to make the whole difference in the next few years. So I like also to introduce myself as a software craftsman, because I believe that we can change the world for the better with what we do with code. So I truly believe that we as software developers, we are the most important people in the world right now, because in the next 1,000 years, no evolution or no revolution is going to happen in this world without a software developer behind it. Because we are going to transform the world that we live right now for the better or for the worse. Because we can make a choice. Sometimes we know that we can make I used to be one of the people that in the past, because of like time or money restrictions, delivered crappy software into production, and I made people miserable. Because we know that feeling of being miserable when we use software that is not up to our expectations. But we can make a choice. We can decide just to improve people's lives with the software that we're doing. We can decide to make people's lives better with the software that we're doing. So I believe that if we're all here today trying to discuss and trying to learn, trying to uncover better ways to deliver better software faster into production, we all made this decision already because we want to change people's lives for the better. Okay, so congratulations to all of us. And if I have to choose just one thing to say about DevOps and microservices in all of these discussions that we have in these days, I have to pick that the most important thing for me in the DevOps and microservices world is what we say, what we call the feedback loop. The feedback loop is like an essential activity that we have in all things that we as humans do, because the feedback loop is the notion that we need to know if we're doing the right thing right. And the more time that we have between having an idea and delivering that thing into production, the worse the quality of the software that we're delivering. So we can shorten the time between, well, maybe I had this idea, maybe I'm formulating some hypothesis to try to solve this problem, maybe I quickly just discard some because this one is going to take too long, this is going to be too costly, this is not going to work, maybe this one or this one that can fit the problem. I just choose one of them, I just test it, how do I know if this hypothesis is going to work? I just code it, and I release that software into production. The more the amount of time that I take from having an idea and try to solve the problem and deliver that into production, the worse the quality of the software. So we need to shorten this time. And technically, the term that we have in the DevOps and microservice world for the time that we have from idea to production is the lead time. But for many people, lead time is like a very abstract concept. So before joining Red Hat, I used to be an independent consultant and so discussing DevOps and microservices. So I always talked to people and told them that the best way for you to try to reduce the lead time in your process, the best way for you to improve the feedback loop in your process is to try to reduce the batch size. And the batch size technically is the amount of changes that you have between each one of your releases. So I like to make a very simplistic correlation. I like to say that people don't release software faster into production because when we release software into production, we have too many bugs into production. So the human way of trying to solve this problem is, well, if we have too many bugs into production when we release software, we need more time for testing. But people don't realize that if we have more time for testing, we also have more time for coding. So if we release software every month, if we release software every 2 months, we have even more bugs into production, right? So the economic way of trying to solve bugs into production is trying to reduce the batch size. So the correlation that I like to establish is that what causes bugs into production? What causes bugs into productions is change. We have usually changes in 3 different areas. We can have changes in code, we can have changes in environment, and we can have changes in state. I'll try to oversimplify that, saying that what causes bugs into production is changes in code. So the more changes in code you have between each one of your releases, the more bugs you have into production. So the economical way of trying to solve this problem is the lesser changes you have into your code between each one of your releases, the lesser bugs you have into production. So until we can constantly reduce the amount of changes, we can constantly reduce the batch size of our releases, the lesser the bugs we have into production. And if we reduce that until the ideal size of 1 commit, 1 delivery, if we just committed 15 lines of code and we deliver that into production half an hour later, if we create a bug, where is the cause of the bug? Is that in that 15 lines of code that we just deployed into production? So it's much easier for us to assess where is the cause of the problem, and it's much easier for us to fix that. In fact, most of the companies that have sufficiently mature software delivery pipelines, it's much easier for them to just spot a bug and release a new version into production rather than having very complex rollback strategies. So we are here to try to reduce the batch size of our software delivery pipeline. But even if we try to reduce even further our software delivery pipeline, there is something that we call the maintenance window, which is that specific time frame of the year or month or week that the ops guys tell us, well, you're only allowed to release your software in this specific time of the day or the week of the year because you are not allowed to disrupt users to production, right? So if the ops guy says, you only are allowed to release your software like once every 2 months, you won't be able to reduce even further your batch size. So if you want to uncouple your software delivery pipeline from the maintenance window, you need something that we call zero downtime. You need zero downtime deployments. But for you to achieve zero downtime deployments, you need an architecture which is called the single requirement for having zero downtime deployment is for you to have at least a blue-green deployment, which is a very common term these days. I'm going to explain to you very quickly, just in case nobody has seen that before. In a blue-green deployment architecture, traditionally, you have like your clients issuing requests directly to your deployment. If you want to create a zero downtime deployment with blue-green deployments, you need to add another component to your architecture, which is a proxy. And after that, the proxy is just a component that is receiving requests on behalf of your backends. Now you have two equal environments, blue and green deployments. Each one of them is capable of handling like 100% of your requests into production into any given moment. So how do I create a blue-green deployment? If I have two environments with the exact same version, if I want to deploy a new version of my software, I just ask the proxy to stop issuing requests to the green deployment. I stop the green deployment. I copy the new artifacts. I start the servers. I wait for the servers to warm up, just in case I'm using a technology like Java, because you need to warm up the server for it to become fast. And if everything went well, I can just start issuing requests to the green deployment. But people don't realize that blue-green deployments are not the only way for you to achieve zero downtime deployments, but it's also the safest way for you to be doing your deployments, because if anything went wrong, you can just decide to not update your blue deployments. So you have a problem in your green deployments, you just need to ask where's the problem with this new version. After everything is right, you can then issue your request to your green deployments. But if everything went well, you can do the same process with the blue deployment. You stop the servers, copy the new artifacts, start the servers, warm them up, and then start to issue requests to your blue deployment again. Okay? And I have to apologize for speaking too fast. I usually don't speak that fast, but I have a lot of content to cover in 45 minutes, so I'll need to talk in this space for the rest of the presentation too. Okay? So, but if you want more details for any of the things that I'm discussing in this talk today, you have everything that I'm talking today in a very detailed version in the book. Okay. And I always like to say that, well, we're thinking about achieving zero downtime deployments with code might be easy. Maybe not that easy, but certainly it's much easier than with the data. So with states, it's much harder for you to achieve zero downtime deployments, because then you need to have two different versions running into production, and the state must be compatible. And when I'm saying state, your state can be two different kinds of states. You can have ephemeral state, which is usually the state that you store in the HTTP session, and you can also have the persistent state. With the ephemeral state, it's hard to, but you can always choose to discard. Well, the user has to log back in again and start over the process. If the person was filling like a 200-field form and you ask it to discard and start it over again, well, he or she won't be happy, but it's manageable. With persistent state, you can't allow to lose any kind of persistent state, and usually this state in enterprise systems is stored in a relational database. So the number one question that we're trying to answer is, what about my relational database? How do I achieve zero downtime deployments when I have a relational database that is persisting my states? And the answer for that is that first, you're not allowed to be issuing your SQL update statements to your database manually anymore. You need to automate everything. So in the Java world, the two most popular database migration automation tools are Flyway and Liquibase. As of this year, both are feature complete. I don't have a strong preference for one or the other. Both solve the problem. I've just been using Flyway because that's the tool I've been using in the past project I've been working with. But you can choose any of them. So after you have automated your database migrations. And just to give you another technical term, migrations is the technical term that we give for the amount of changes that we have between each one of your releases in your database schema. So that's the usual SQL statements that you have your outer table, your update things, or even your Java code if you need to perform some complex calculations to update the database values. That's what we call migrations, okay? So if you want to achieve zero downtime migrations, the secret sauce is that they need to be back and forward compatible, which means that each one of your versions needs to be, of your database schema, need to be compatible with the previous version and with the next version. And for us to be able to achieve that, we need to stop issuing like migrations with like 100 database statements, like 100 outer tables, adding a lot of columns and updating a lot of different fields in your database. You need to split them into baby steps, which means that we need a smallest possible batch size, which also means that for many, if not all of the use cases for zero downtime migrations, each one of your migrations will have a single SQL statement. Just one outer table, just one update or something like that. You also need to avoid long locks. So if you have like a table, sorry, with like a billion rows, and when you issue an updated statement to this table, it takes like a lock time of 5 minutes. You're not allowed to do that anymore because 5 minutes, maybe it's too much for your downtime into production. Then maybe you need to shard your updates. Well, maybe I'll need to update my database table with like 1 million rows every time, because then I'll have like just 2 seconds of lock time, and 2 seconds is a bearable amount for me in this particular use case. Okay, so you're going to have to split your updates, which technically in the database world we call sharding, which is a very fancy word for just saying splitting your update statements. And in the past, if you used to issue like something like outer tape, something, rename column, something to other thing, maybe you have to split and change your schema migration to a lot of multiple statements, and each one of them will have to be issued in a different release. So I've been able to discuss this problem with many different teams worldwide, and to be very honest, most of the teams that were doing this kind of things were startups because they had a very mature software deployment pipeline. And the most common scenarios that I've been able to collect worldwide were these 4. Add a column, rename a column, change the type and format of a column, and delete a column. These are the most common database migrations with zero downtime that I was able to collect. You might be thinking, what about a table? Well, if you think of a table as a collection of columns, you might be able to reapply all of these schema migrations multiple times until you achieve what you want. And I have to tell you that you might think that what I'm going to show you to you is a lot of work. In fact, in the beginning, it might look like a lot of work, but the secret for zero downtime migration is that you never issue a destructive statement into your database into production. So you always have the previous version of the data available for your previous version of software that are running into production. But it also means that since no statement is a destructive statement, is also the safest way for you to be releasing your migrations into production. You never lose any data, so it's much easier for you to rely on this kind of migrations rather than have to rely on a backup that sometimes take like 8 hours to restore into production, as I did once myself. Okay? It's not a very happy scenario. So how does it work? I'm going to cover very quickly, but again, if you want that in more details, you can read that in my book. And first scenario, trying to add a column. Each one of these steps, 1, 2, 3, and 4, is a different release of your software into production. So if you just want to add a column into your software, first release, you're going to outer table add column. Second release, your code computes for the read value and writes to the new column. And computing means that if you have a default value, you just assume a default value. But if you can compute your read value from other fields of your database or from another source of information, you're going to do that and assume this read value. Third release, you updated data using shards. So if you're going to have a lot of new values in your database, you need to update them to your default value of your computed value. And fourth version, your code finally reads and writes from the new column. If you're updating your database with this kind of migrations, you're going to achieve zero downtime migrations because each one of your releases is back and forward compatible with the previous version and the new version, okay? This is the simplest possible scenario. Next scenario is rename a column. So you're not allowed to just rename a column anymore. For you to rename a column into production, in first release, you alter table add column. Second release, your code reads from the old column and writes to both. Third release, you copy the data using small shards. Fourth release, your code reads from the new column and writes to both. Fifth release, your code reads and writes from the new column. And sixth release, well, you might delete the column. You don't delete the column immediately because deleting the column is a destructive statement. You never delete a column into production. When I say delete a column, you just mark the column for deletion. You just create a Jira ticket to your DBA. And after that, in the maintenance window, which can have like 6 months, 3 months, 3 weeks later, your DBA is going to check, well, nobody's using that column anymore. Maybe it's safe for me to delete the column after performing a backup, okay? So these are the 6 steps for you to achieve zero downtime migrations if you want to just rename a column. And next scenario, change the type and format of a column. You can see a pattern here. It's exactly the same step. So if you want to rename a column or if you want to change the type and the format of a column, that's exactly the same steps that you need to apply when performing zero downtime migrations. And last step, deleting a column. You never delete a column into production because that's a destructive statement. If you delete a column, you lose the data. If you want to roll back your version, you screwed because you don't have the data anymore. So if you want to delete a column, well, first you don't. You just mark the column for deletion. And the next version, you stop using the read value, but you keep writing to the column. Because if you need to roll back, your previous version still needs the value that is in that column. And much later than that, if you decide, well, nobody is reading the value from that column anymore, and many releases later, you can just decide to stop writing to the column, and the DBA can safely remove the column from your database because nobody will be using that value anymore, okay? So that's the 4 basic scenarios for performing zero downtime migrations. And some people might ask me, what about referential integrity constraints? Well, there's no easy answer. Sometimes you need to break some walls to make room for improvement. So you need to drop the constraints and recreate when everything is done later. And the same applies for no constraints, for example. Okay? So, and why did we discuss that? Because this is a microservice talk. Why have we discussed zero downtime migrations? Because in the past, the downtime of your system used to be the downtime of your monolith. So if you're performing on a release and you had downtime in your monolith, it was equal to the downtime of your system. But now that we have a microservice architecture, we have multiple components, and each one of them has its own database. So we're not allowed to have downtime in our system just because one tiny little microservice is updating their database schema. Okay, so we need to improve our overall uptime. So now zero downtime migrations are so important. So that's why in the discussion about microservice databases, I stumbled upon this discussion of zero downtime migrations. And that's why I chosen to show you, because it's a very important thing that teams are doing to achieve zero downtime deployments with microservices architectures. So now we're going to dig into the microservice part of the talk. And Martin Fowler did a very nice job collecting some of the characteristics of microservice architectures in his Blick. But today, we only have time to discuss this one, which is the decentralized data management principle, which basically states that each one of your microservices must have its own database. Okay? If you want to know why, maybe you can read the Blick later, because we're going to dig into more problems. And again, if the best practice is to split your monolith into your microservice architecture, and each microservice must have its own database, how do I get an old legacy monolithic database and then split that into microservice databases? So I still have a monolithic database, and the answer for that is for some time, both your monolith and your microservice will be needing to read and write from this exactly same sort of information. And maybe you need to transform the information that is being read and written to your to and from your database. So I can't help you with trying to answer the question, which piece of my monolith is the ideal candidate for me to split, because basically that's a business model problem. I have another material that I'm preparing, trying to show how you can split like your old legacy monolithic application, starting from code and with the data too. But basically, it's a business model problem. I think that domain-driven design and bounded context help a lot you to decide which piece of information are you going to split. But after you decided which piece of information you will be better for you to split, I can help you on how to integrate the data and how to make your microservice and monolithic architecture work with this split information. Okay? So splitting is not easy, but how do I integrate the data later after I decided which piece of information must I split? And before I dig into the integration techniques, I'll have to explain to you very briefly some concepts. First of all, consistency models, and I'm going to explain to you an oversimplification of these concepts. I'm only going to explain you strong consistency and eventual consistency, and not just pure eventual consistency. We're going to explain to you strong eventual consistency, okay? So in a strong consistency model, if I have like multiple nodes in my system, like like one monolith and 4 microservices in my architecture, in a strong consistency model, if I have like everybody has a variable named I and I equals to 3, and I decided to update my value to 5, so everybody on the system needs to agree on the new value before any client can read the new value, okay? So if I equals to 3 and I decide to update I to 5, everybody on the system needs to get updated to 5 before anybody can read the new value. Okay? That's a strong consistency model. That's the model that people think that is applied when we're using like database transactions or distributed transactions. I'm saying think because strong consistency, pure strong consistency, is very rarely used in the real world, but that's a model that we use to learn, at least in school. So when I say strong consistency, you would just assume that that's the model that we're using. And we also have eventual consistency. And in pure eventual consistency, you can update any node in your system. And if you allow like multiple nodes to have simultaneous updates, you might have data conflicts. So in distributed enterprise systems, the model that we usually choose to have is a strong eventual consistency, which is that if you have 5 nodes in your system, you choose just one of them to be the canonical source of information in your system, which means that this is the only node in your system that is allowed to have updates. And usually it's true because if you decide to split the customer information from your monolith and you create a customer microservice, usually the customer microservice will become the canonical source of information because that's the only endpoint in your system that is allowed to receive customer updates. So if you decide, well, this is a canonical source of information, I'm only allowed to do updates here. But then, if I have like everybody I equals to 5, and I decide to update I equals to 7, if anybody is reading the value from here, it has already received a new value. But other nodes in the system, they might have outdated values, but all the values are always correct. So I updated I equals to 7, so everybody must have like 5, still 5. So this node, maybe I have already updated that to 7, so people reading from this node are receiving 7. And maybe I already updated this node to 9 already. So in my system, I might have nodes with different outdated values. So maybe some nodes have still 5, some nodes have 7 already, and some nodes already have another new value, like 9. So in a strong eventual consistent system, I have nodes in the system with different values. All of the values are correct. They just might have different timestamps. So they might be outdated in different moments of time. That's a strong eventual consistent system. And that's usually the model that we're going to apply in distributed enterprise information systems. Okay? Another very important concept that I have to explain to you is the difference between CRUD and CQRS, because people are using CQRS to mean different things these days. And I'd like to tell you that CQRS is a very simple architecture. You just didn't know that CQRS had this name. So first, I'll start with CRUD. CRUD is a very simple model. In a CRUD architecture, you use the exactly same model to perform all your operations. Create, read, update, and delete, which means that both read and write operations are using the same model. When I'm saying same model, I'm saying that you're using the same code model, you're using the exactly same set of classes in your application, and you're using the exactly same set of tables and columns in your database. You have the same data model, and you also have the same domain model in your code. That's a CRUD architecture, exactly same set of classes for reading and writing. But then CRUD is a very simple architecture. It's the most appropriate one for like 90% of the case. It's also so simple that most of the tools that we use these days can scaffold automatically most of the code for us for a CRUD architecture. But then you start to have some challenges, and that's when CQRS applies. CQRS is a very fancy name for Command Query Responsibility Segregation, which just means that now you can have different models for reading and writing operations. Let me explain that to you. If you have a customer architecture and you have a customer object, a customer class, and you populate all the fields to try to save that to your database, but of course, customer can have like your ID, name, telephone history, address history, shopping history, a lot of different data on the customer information. And maybe somebody asked you to generate a customer report. In the customer report, you only need the customer ID, the name, and the current email address. So you don't want to query all of the customer information from your database, populate that in objects in your memory, just to generate a report with 3 different fields. So what do? You create a class called a customer DTO, which just holds the information for ID, name, and email address. So when you create a customer DTO class and you create a custom query that is only going to fetch these 3 fields from your database into memory to generate your report, congratulations, you just created a CQRS architecture because you're using a customer class for your writing operations, your insert and update operations, and you're using the customer DTO class to generate this reading operation for this report. And later, if you have another business requirement, well, now I need another report for a customer. I need a report that has the ID, the name, and the telephone number. You're going to create another class, which hopefully you won't name customer DTO2, okay, for this specific report. So you have different models. You can have multiple different models for reading, but you usually only have one model for writing. This is the CQRS architecture. This is the simplest possible CQRS architecture. But after you start doing that, you realize that you're not constrained to have just a single database for your reading operations. So if you ever created a database view and you issued requests, queries against your database view, congratulations, you created a CQRS architecture with different data models. So you're writing from one set of tables and columns, and you're reading your information from another set of tables and columns, and using also a different code model, different sets of classes for the reading operations. So you're creating a CQRS architecture with different data stores. And these different data stores can be like something like views or database materialized views, which is are very used for like aggregation reports. That's a CQRS architecture with different data stores. And this is the most common architecture if you're using relational databases with distributed systems such as microservices architectures. This is the alternative that we're going to explain to you. Okay? And also, I have to explain a bit of CQRS and event sourcing because many people advocate that event sourcing is the solution for all of your problems when dealing with distributed systems. I have a different idea because I've been helping teams to work with event sourcing and microservice for quite some years, and many of them, most of them have problems with event sourcing, particularly because it's very hard to do event sourcing properly. Okay? But what is event sourcing? Event sourcing is a very fancy name for architecture where the state of your data is not stored in a single database table, a row, and a column. In an event sourcing architecture, and the classic example that I'm going to give you is a bank account. Okay, so you never store the amount of money that you have in a bank account as a single column in a database. What do? You just model your domain model so that the amount of money that you have in your bank account is represented by a stream of events. So how do? If all of the bank accounts start with a 0 amount of money, you just create debit and credit events. So if you want to know, you just apply debit and credits. And if you want to know how much money you have in your bank account, you just have to start from 0 and then apply the multiple debit and credit operations. If you compute all of them, you know how much money you have in your bank account. So this event sourcing architecture is it's an architecture that you have very fast writes, but you can realize that you have very slow reads, because every time you want to know how much money you have in your bank account, you have to start from 0 and start applying all of the transaction history, which takes longer the more transactions that you have and the more customers that you have in your system. So that's why event sourcing architectures, which is the amount of money that I have, is not a column in my system, is a stream of events, is usually tied to CQRS architectures, which means that the canonical source of information is the transaction log. But since it's too slow for me to read information, I create a CQRS data store, which is another table with another column, which holds a cache of the current amount of money that I have in my system. So that's what you see. Sometimes if you go to the bank ATM, you just withdraw some money, and then, well, you just withdraw like 10,000 dinars. But you get your mobile phone, you check your bank account, well, I still have my 10,000 dinars in my bank account. Because that's an eventual consistency system. You just added a transaction log, which is going to be propagated in your system, but the cached information in your bank didn't propagate to the system from your mobile account yet. So that's how it works with event sourcing and CQRS. And if you're thinking, well, this is eventual consistency thing, doesn't work in the real world, I have to tell you that most of the systems that we're using today are already eventual consistent. We're just not used to be thinking about eventual consistency every day. But if we're dealing with distributed systems, that's the first consistent model that you're going to have to apply in your world, because strong consistency is very hard to achieve in a distributed system, okay? So CQRS, event sourcing, that's why usually when you have an event source system, you tie that with a CQRS data store, because you want read data stores, cached read data stores for performance reasons. And we're going to use CQRS read data stores for integration issues in the case of microservice architectures, okay? And before I explain to you these 9 different scenarios from database integration, I have to explain which is the typical integration scenario when people decide to extract your database from your monolith. People realize, well, I have a monolith, I'm going to extract my customer microservice here, so I extract the customer tables and columns from here, and I create another microservice with a separate database for that. So since I've created a very nice architecture, all of my requests for customer information are going through a DAO. So everything I need to do is, well, I have a customer microservice, I create a REST endpoint. So my DAO now, instead of issuing queries directly to the database, is going to issue HTTP requests queuing for JSON or XML from my microservice endpoint. They deployed that into production, and they fail, because they realize, well, it's just too slow to perform that into production. Well, if it's too slow, we have a performance problem. How do we solve a performance problem? With cache, right? So they created an internal cache in their monolith, and they realized, oh my God, my internal cache is not big enough to hold information. What did? They created an external cache service to store the information. Now they have much more problems than before. But now, well, now the performance is reasonable. But then they realize, well, in the past, I don't need just the customer information, not just for reading and writing. I have a lot of different reports in my system that are still used to join all of the customer information in a SQL join. Now I have to query all the information from the database from the other fields. And I have to join the customer information in memory, because when I have the customer now, I'm joining objects, and for the other kind of information, I'm joining tables. So I have to join everything in memory, and it just takes too much long for me to refactor all of my system for me to generate the exactly same old reports. Then, why are we creating a CQRS that is stored as an external cache in a key value database? Why can't we create our CQRS that is stored inside my old relational database? So I create a copy, a cached copy of my customer information from my microservice to my old monolithic database, and I can still keep the relational joins, my SQL joins that I used to have. That's the typical path that every single team that I visit performed in the past. So they start a REST endpoint, doesn't work, internal cache, external cache, CQRS that is stored inside your relational database, because then you can keep the legacy thing working without disrupting other parts of the system. That's the way that people were doing in many different enterprise systems, and that's the way that they are creating this CQRS data store, this CQRS read data store in their monolith. So the scenarios that I've been able to collect worldwide were shared tables, database view, materialized view, triggers, transactional code, ETL, data virtualization, event sourcing, and change data capture. Okay, so I have to explain to you very quickly because I only have 6 minutes left, less than that. And not all of them I consider to be best practices. In fact, some of them I consider hacks, but people were using that in production, and they have been to a certain extent, they have been successful. So that's why I described it here. First integration, shared tables. It's the fastest data integration technique possible. You always have strong consistency because you're reading from the same database with transactions. It has low cohesion and high coupling because you're reading and writing from the same set of tables from both your microservice and your monolith. In fact, I think this is it needs to be considered a hack because I've seen that as a perfect excuse for not changing anything anymore. Because when you have a monolith and a microservice, it's different teams. And, well, the microservice team, I can't change the database because the monolith needs that. And the monolith team, I can't change the tables because my microservice needs that. So you get stuck forever in that scenario. So if you choose shared tables as an integration technique, just do that as a hack, knowing that in the next version, you need to fix that. Because you're not going to be able to change anything anymore, ever. Second integration technique, database view. It's the easiest one to implement. It's the largest support from a DBMS vendor. You might have possible performance issues. You also have always strong consistency. One database must be reachable by the other, which means that at least for Oracle, you need to create a DB link. And I know some DBAs are going to curse me for that. But I've seen people using that in production, and it works depending on your staleness requirements and your performance requirements. Okay? So database view, I have my microservice, I have my monolith. I just project a database view in my monolith so things can keep working, but I always update the information using my microservice database. That's one way for me to perform. Materialized view, if you had performance issues with your view, maybe you want to consider creating a materialized view, which is most databases implement that as a physical table. It's just a fancy way of creating your copy table. It can be updated automatically. You can have strong or eventual consistency. Depends. If you update your materialized view on commit, is strong consistent. If you update that on demand or on a cron trigger, it's eventual consistent. Usually it needs to be eventual consistent depending on your performance requirements. Again, one database must be reachable by the other. At least on Oracle, it's possible using a DB link. And it's updatable depending on DBMS port. But I really don't recommend for you to have like more than one source of updates in your system. You usually have to choose just a single canonical source of information. You can also have database triggers, which means that whenever I write here, I'm going to update my CQRS data store in my remote endpoints. This trigger also, I consider that a bad practice because it only works with single endpoints. If you have just one single microservice and one endpoint such a monolith to be synchronizing, it's okay. The problem is that if you have multiple endpoints, you have to code point-to-point integration information into the trigger. So whenever I write here, I have to write in multiple different endpoints. If I update there, I have to change here. And if I change here, I have to change all of the tables in all of the other systems. Okay? So triggers is a bad practice. I don't consider that to be a good practice, but some teams are using successfully that. And it's only feasible for point-to-point integration. The same applies for transactional code, because if you're using triggers for updating your remote CQRS data stores, you can also use distributed transactions and store procedure for achieving the same result. So I also consider that to be a hack, and it's only feasible usually for point-to-point integration and not multiple endpoint integration. ETL tools, you can also use ETL tools, like some people call that business intelligence tools, such as ClickView, Pentahole, Dashbuilder, which are usually like report generating tools. You can use ETL tools because you can they just extract information from a database and write that to another base as a source of information. So you can create your CQRS data store using ETL tools too. You have the most amount of possible tools available for you. Usually you can update your database using a button or a cron trigger. I consider this to be feasible if you already have an ETL person in your team, if you're already performing multiple ETL integrations, and it's just going to be one more ETL integration for you to perform. But if your microservice architecture start to grow, then ETL is not a feasible option anymore because you need to manage these kind of things. If you have multiple teams doing this kind of integration, you need to change to a more robust integration. You can also use data virtualization, and I'm going to show you very quickly this. Data virtualization just means that you have your physical database, you create a virtual database on top of that, and your client is issuing requests. Virtual database is a very safe approach for you to be creating because one of the problems that we have when we're extracting my Microservice database, at most of the times we do it wrong. And if we do it wrong, it's very hard for you to put information back. So if you create a virtual database, you can just hack on your database and just play with your microservice architecture. If you did anything wrong, you just can discard your virtual database because the physical database didn't change at all. So I've never seen a team using database virtualization just for microservice architecture. The two teams, in fact, this week I learned about another team, so now I have 3 scenarios that people use database virtualization for that. So they already had database virtualization, and it helped a lot for them to create their microservice architecture because it was very, very safe. They could play a lot with the information. Event sourcing, which I've just described to you. And as I said, event sourcing, some people advocate that as a solution for all of the problems because, well, event sourcing, I can use distributed messaging for that, so I have a low coupling in my system. People don't realize that when you have like your code, the coupling in your application is the code that you have between each one of your endpoints. But when you're using event sourcing and messaging, the coupling between your system is the type and semantics of your messages. Every time you change the type and the semantics of any messenger systems, you created a cascading change. So I added another event. I have to change all the endpoints in my system. I change the type of my message. I have to change all the types in my systems. And it's very easy for you to get it wrong. When you have a monolith, you can refactor your code with your IDE. If you have a distributed system with distributed messaging, you can't afford to do that. You have to change that in every single endpoint. So that's how it's very hard. And the coupling exists, and if you do it wrong, it's very hard. And the last one, very quickly, I have to tell that one of my favorite ones is Change Data Capture, which is a tool that is not widespread as I thought it would be. Change Data Capture is a set of tools that plugs directly into the database. So instead of, if you don't want to mess with your legacy monolithic application, you can instead just plug directly in your database, and the CDC tool starts to read directly from the transaction log. So for every insert, update, delete, and alter table information, the CDC tool captures that, creates a message, and distributes that in your message system. So that's the typical CDC tool. Anybody here ever used Oracle Golden Gate? 2, 3? Okay, I never use Oracle Golden Gate because they tell people that it costs like you 2 kidneys. But Oracle Golden Gate does much more than that, but Oracle Golden Gate also has CDC features. But what I wanted to show, I'm over time already, I just want to mention to you, there's a very nice open source CDC project, which is called Debezium, Debezium.io, which is an open source and free, of course, CDC tool that is available for you. Right now, Debezium supports MySQL, PostgreSQL, MongoDB. We have like almost complete support for Oracle, and the next one might be SQL Server, but it's an open source project, and I can disclose more information. And it's sponsored by Red Hat. So if I had time, I would show you a Debezium demo, but not today. But if you want to have more information, I'm available later for questions, okay? And that's what I wanted to show you today. If you have, all the things I said are available on the developers.redhat.com website and blog. And if you want more information, I would love your feedback. The easiest way for you to reach me out is at my Twitter handle at Yanaga. And again, thank you very much. Thank you. Oh, I have some books if anybody wants to get. I think I have some copies here.
There are some questions, but you can approach him afterwards, and please don't forget to rate. So.
Okay, yes, I have a special request. Very quick one. May I take a selfie with you? Because I need to show my family that I was here, okay?
They will not believe him. So.
Yeah. I'm in Belgrade. Yeah. Hey! Thank you very much again.